Alright, so there's my email address if you want to email me after talk. It's also on the last slide. So just before we begin, I want to make clear that the language for specifying these 3D graphical effects that I'm going to show you in this talk is Connell Elliott's work. And I've just done this front end recently, which basically is written in Haskell and Cocoa, and I've used the foreign functions basically to communicate between the two. A few years ago I also did one that was a web app, so it was a Yesod web app which produced JavaScript, which then ran WebGL. But you require OpenGL, specifically the GLSL, the OpenGL Shady language. Any mistakes I make in explaining Connell stuff in mine alone, and there may well be some of those. But I'll start with the 2D stuff, because I think this is a really good intro into how you might specify images functionally. And you might be familiar with this work already, so feel free to fall asleep until the 3D part, if that's the case. But the idea is that images normally in computer graphics we're concerned with pixels and color formats and a whole lot of implementation details that aren't necessarily that interesting. And of course you need this for efficiency. But if you were to discount efficiency and then just look at maybe composing together images in a functional way, how would you go about it? If efficiency wasn't a concern, how would you go about it? What might be an interesting representation for images? Well, what we might want to do is say that images are simply functions from points which are Cartesian coordinates, x and y coordinates, to colours, which can just be something like this, an RGBA format. Let's clamp it between 0 and 1 for each of the RGB and the alpha channels. What's interesting about this is that it's not discrete at all. So this is these are continuous Cartesian coordinates, and that means, well, okay, I'll get on to that. Okay, and I'll go straight to it. That basically means that you can pan and zoom arbitrarily. It means that these images are resolution independent. If I define a circle as being all those points that, for which x squared plus y squared is less than 1, then what I can do is I can sample that function arbitrarily at any resolution. So I can zoom right in on it, I can zoom right in on the corners, the edges of it, and it will get smoother as I do so. So I'm never, I can produce an image as nice as I have computational resources to do so. So 2D images specified this way have a really, really basic implementation technique, which is, choose a resolution that you want the final image to be, say 512 by 512 pixels. Choose an interval on the actual image that you want to sample over, so that could be between -1 and 1 on the x and y axis. But it could be anything. And then you iterate over the rows and columns, and at each xy calculate image xy and translate the color result to some color format of your choice. You could render to the screen, or you could render to a PNG file. It doesn't really matter. But honestly, you can get away with writing a simple renderer in a page of code in Haskell for this, which isn't true in the 3D case, but that's why I started with this example. So I just thought I'd show you an example. This is a very small rendering. The interval in this one's -1 on both, -1 to 1 on both x and y axes. Thus, I'm sampling in 1/8 size chunks. So 8 from -1 to 0 and 8 from 0 to 1. And I'll sample in the middle of the pixel, i.e. 1/16 into the chunk. And so the 16 values that I'm going to sort of sample out are these ones. So here's an image. So I don't know what this image is. Let's just treat it as a black box, okay? But the result of applying image at these two coordinates is 1001, which means it's completely opaque and it's red. And then here we get it's 1011, which means it's magenta because it's the red and blue components. And that's now at -13th of 16. And so on. And if we just continue this process, we can generate an image that way. So, were we to define a circle this way, well, okay, let's define circle this way. So it's what I said before, if x star x plus y star y is less than 1, then black else white, okay? And this is the definition for black and white. They're both opaque. If we do that, and then we render that 16 by 16 pixel image again, actually this one's on -2 to 2, so we're kind of zoomed out here. That's exactly what you'll get. And you can kind of prove this to yourself. If you were to take the square of that and add it to the square of that, you'll find that it is just less than 1. And if you take the square of that, and add them together, you'll find it's just greater than 1. And that's why that's white. But then, of course, we can zoom in to another interval and then sample it again. Anyway, that's just 2 images. That's fairly straightforward. So, before we get into the 3D stuff, a couple of days ago I decided to extend this idea to sound, which I actually did as an experiment, I don't know how long ago, maybe 8 years ago, but I'll just do a live demo for this, if you don't mind, and then play you some sounds. So I've called this module Fun Sound. Let me just mirror. Okay. Now, would you like me to increase the size of that? Is that okay? So everyone can see that? Okay. So, what we're doing here is it's similar to images, except now we're going to model sounds as functions from time to amplitude. Okay, fairly interesting way to do it. And again, it's continuous. So time is any value from, well, actually, it's not just positive values; it can be negative as well. But that doesn't really matter. And amplitude's going to be between -1 and 1. Okay, so the max size of the wave is 1. Max amplitude in positive or negative direction. And then we can define a sine wave this way. Just to say it's for a given frequency, then when we sample it at a particular time, then return sine of 2 times pi times the frequency times the time. And that'll just be periodic. And then what I have here is a combinator for adding 2 sounds together. Right, so that's just the 2 primitives I'm going to use for this little talk, but you could create all sorts of combinators that could do all interesting things. You could have one that sequenced 2 sounds together, for instance. You could fold a whole bunch of sounds together. You could halve the frequency, you could double the frequency, do all sorts of things. And they're all really, really easy to program. In fact, I might do one that modifies the frequency, scales the frequency, just for fun. But first we'll play some sounds. So let me see if I can find where I did my test put. That's fine. Okay. So I have not factored out this code at the moment. So this is just some code to produce a WAV file. actually run fun sound. Okay. So that's kind of boring, but that's just a sine wave sound. Okay. Yeah, okay. There we go. I wish I could make that louder, but you can't hear that. So now you might want to do something like add some sounds together. So this here, if I add these three together, and it's just three different frequency sine waves, it'll actually produce the dial tone that we're all familiar with. And that'll be the end of my demo. There you go. So let's just kind of look at what add sound did there, and just think about what actually happened. So it's a combinator which adds two sounds together, and we applied it twice. What we do here is we take sound and sound prime, and then what we do is we return a function, and probably better if I actually write it this way, as a lambda. Just make it a bit more clear what's going on. So the thing on the right-hand side now is a new sound. And it's a new sound, which of course is a function from time to an amplitude, and all it does is just add the two other sounds together at that time and divide by 2. And then you can do that as many times as you want. And produce, arbitrarily complex sounds. I did have a musician friend who I got to test this out when I first met a few years ago, and he produced some really interesting soundscapes that kind of merged into all these different sounds and sounded very different to sample-based music to me. All right. So I just have to wish there was an easy way to switch between mirroring. Okay. So, introducing Shady, a language and compiler from Haskell to GLSL. So now we're extending into the realm of 3 dimensions, the third dimension. So, I guess you have 2 choices of how to do this. One would be, I guess the natural extension of the idea would probably not be the one that Shady does. So the natural extension of the idea would be, well, if an image is a function from 2 dimensions to colours, like an XY coordinate, then a 3-dimensional image would be one from 3D to colours, so X, Y, Z to some colour. But in order to do that, you have to do volume rendering, and then you have to think about, exactly how you're going to render that. Which, I'm not saying that isn't possible, and it's something I'd be interested in looking at in the future, yes.
I want to see your Haskell implementation of Minecraft, like Haskellcraft, I think next week. Next month.
Is that volume rendered?
Oh, yeah.
I guess with the cubes are pretty big.
Yeah.
Really big voxels.
Yeah, right. Yeah, next week, okay. Yeah, no problem. So, except OpenGL and GLSL in particular works really well with polygons. So what it does instead is produce what's called a vertex shader and a fragment shader. And the vertex shader is responsible for deforming a mesh into some shape. So the mesh is just made up of triangles and then gets deformed into some shape, which is the final surface. And then you texture map one of the 2D images that I showed you before onto the surface to get the surface effects. And you can also do some lighting as well. So a surface is, okay, I'm just going to use R as a shorthand for the reals. It's implemented with floats in GLSL because at least for the version I'm using, they can only handle floats in that language. I do think some of the newer hardware actually has double precision stuff, but it's not that important. Anyway, so that's going from XY coordinates, because it's a mesh, it's 2D, it's just 2D mesh, and then it deforms it somehow into R3. So each vertex in the mesh gets shifted from a two-dimensional plane somewhere into a three-dimensional space. Okay. Another concept you might want to talk about is a height field, where it's a function from 2D space to just one-dimensional space. So that there is kind of like, at this point here, how high is the surface above, how high is it above the plane or below the plane? So you could put a sine wave through it or something like that. And that would create something kind of interesting surface. Or it could be a slope, or it could be an arbitrary surface, but it's defined as a height field rather than this way. But then we can easily convert between a height field and a surface by just applying this function here. So that the field is this function field, it's this term field, and then for a given UV or XY, you produce a UV and then field applied to UV. And then that's how you convert that to a surface. And then we have this notion of, well, you can create surfaces by rotating a two-dimensional curve in the third dimension. So to create a sphere, you could create a circle and then just rotate it, right? And then if you just do one continuous revolution, you create a sphere. So that's another way you can create a surface. I haven't shown the implementation of how revolve works, but it's actually quite straightforward. And here is a torus. So a torus is just a donut. It's the world that Pac-Man lives on, if you didn't know that. It never falls off the edge, it just comes around the other side. What we have here are two radii that define it. So one is the radius from the center to the center of the donut thickness, okay? And then at that center you draw a circle, and then what you do is you rotate it around so that it forms a donut. And that's done using this revolve combinator. And then all you do is you just basically translate, for a given point, you translate from the origin by the first radius. And then you draw a circle there, and then the circles in Shady are defined to be of unit size. So you probably want to scale that to some size, some arbitrary size. That's what the second radius is for. And then you revolve that around in the third dimension, creating a torus. And yeah, I said I'm lying a little bit about the real types here. They're not much more complicated, they're just parameterized. And I thought I'd leave out extraneous detail. Okay. Right, okay, so I'll just give you a quick introduction to... Oh, sorry, a question?
I just had a question about the revolve there.
Yeah.
So, you're not specifying any number of steps that you're revolving around or anything, so you're not actually talking about sort of polygons that kind of,
yeah.
Right, you're just sort of, it's like an abstract notion of...
Yeah, it's a really abstract notion. That's right. So the implementation all comes at the end. So we remained abstract until the point where we compile it down to the renderer. And then, by necessity, that depends on the density of the mesh size. So if you don't have many polygons in your mesh, then it'll generate a pretty chunky object.
Sure.
Yeah. So this is just an abstract notion. But what it really is it's a function which takes this 2D curve, and then what it actually does is it finds out what the that gives you your x and y, and then to get the z, you you revolve around in the third dimension by an amount proportional to the y or the x value. It doesn't matter, because one thing I haven't told you yet is that you sample from -1 to 1 in this world. And so you just multiply that by pi, and then revolve it a certain amount around, and then that'll give you one complete revolution.
Okay, cool.
Yeah. So that's a great question, though. because I did really want to make it clear that this is just continuous at this point, and that the rendering happens later. So GLSL, which is actually the target of these effects. So basically, an effect like this one, you have to just feed it into the renderer, and out comes this GLSL program, and then you compile and link that, and then display it in an OpenGL context, basically. Okay, so a vertex shader, as I mentioned earlier, it's responsible for taking an array of vertices, 1D, 2D, or 3D, and transforming them into an array of 3D vertices. But in Shady's case, it's taking a two-dimensional mesh and turning it into, producing a 3D coordinate, but it doesn't have to do that. And a vertex shader can handle more than one mesh, but we're only using one. The fragment shader is responsible for texturing each polygon. I'm not really going to talk much about texturing in this talk, because I think the surfaces are more interesting. So, in GLSL, there are three types of variables, and they're called uniforms, attributes, and varying variables. And this only applies to version 1.2. I think it's up to 1.5 now, or even further, maybe on computers. But sorry, OpenGL ES I think goes as high as 1.5, and then it maybe goes higher than 1.5 in OpenGL proper. But this is only 1.2. So these uniforms are values which are basically constant over one render, so just one frame of this thing. And Shady uses uniforms in order to sort of transmit useful data like the radius of the circle or however your surface is defined. It may have a certain number of variables which influence how it appears. Attributes vary over all the values in an array, and the attribute is the variable which you use to find out the current mesh vertex. So what basically happens since graphics cards work in parallel, have a lot of little processors, basically each one of them, the renderer is run once in each processor on the GPU, and performs a whole bunch of things and produces a result, and then it's the aggregate result which produces your object on the screen. And then finally we have these varying variables which allow communication between vertex and fragment shaders. So it's always strictly output from a vertex shader into the fragment shader. And why is this important? Because in order to do lighting, you may want to know the normal of a vertex, okay? And that's something which requires the vertex value. So you basically pass that out of the vertex shader and into the fragment shader. The interesting thing though is that the fragment shaders are actually per pixel, whereas vertex shaders are per vertex. They are actually per pixel, and so what happens is that the varying variable is interpolated as it moves around inside, as you basically texture map onto the polygon. Right, so here's a real vertex shader produced by Shady. It's probably too small, isn't it? This was bound to happen.
It's alright, it's not functional, so we shouldn't be reading it anyway.
And not only that, yeah, okay, it's too small, we'll skip over it. If you were to look at it closely, you'd notice some artifacts in it which make you realise that this is generated code and not written by a human. Yes?
Until it runs out.
Ah, sure, okay. We could stop it now and then have a break. This is a 2D effect, but it is implemented in WebGL. Oh, sorry. I could show the whole thing. But anyway, so it uses the same sort of principles so that you can actually move this around and you can zoom in and out on it. And it's functional, like, meaning that if I continue to zoom in on the edge, it just gets more and more resolution, which is kind of nice. Okay, now for the magic. There's an infinite number of them now. And then if I do this one more time, I map that infinite this is just the effects that I created, okay? I mapped the infinite plane, that infinite field of hearts back onto a heart. And you can zoom in on the edges and see that it keeps going. And I can even go 2 more levels deep and... You know what's brilliant about this is you're just composing functions. That's all I'm doing. There's some real power here, right? Just composing the function with itself, basically. The annoying thing is if you do keep zooming in, you think, oh yeah, well I can keep doing this forever, and I can do like a really cool fractally type zoom thing. And it's still looking good, but there's where it starts to stuff up. And that is where I have reached the limits of floating point precision on this computer. Doubles would give me a little bit more, but still not that much more. So the only solution really would be to implement some kind of exact real arithmetic, which I think is probably now more feasible because of the processing power that we have in modern computers. Whoa, there you go. Yeah. Okay.
Would you say you're keeping it real, Sean?
I don't know how to respond to that. I always keep it real, but I never go too far. And there's the broken shader, and that's kind of pointless. So I thought, as an aside, if you're interested, I'd also talk about derivatives. So in order to find the normals at each point on a surface, you need to be able to do differentiation. Okay? And Connell has also written, aside from this work, a wonderful library called data.derivative, which produces an infinite tower of derivatives, and it's exact differentiation. It's symbolic differentiation rather than numeric. And you can see his paper, Beautiful Differentiation. So can I just sort of gauge your interest in seeing an example? Yeah? Okay. All right, cool. I will show you. This is getting a little bit annoying. All right, so I'll open up Beautiful Differentiation, and I'll just show you an example. So I just import these 3 libraries. One of the results of this work is that he generalizes the notion of derivatives. Like usually when you learn it in school, you know, there's derivatives of like 1-dimensional functions and then 2-dimensional ones and so on, and then higher dimensions, and this notion of partial derivatives, etc. But he actually found a way, I shouldn't say Connell found this, he found the work of a mathematician called Spivak, who had generalized differentiation just to linear maps in general, and made his library fully general, which makes this derived basis thing a bit funny, but we'll be ignoring that for this example. So here I define a function which is just sine, and it takes a double and then produces one of these things which is basically a tower of derivatives. So the thing on the right is the value and the type of the value, and the thing on the left is the type of its derivative. Okay? In this case, they happen to be both the same. But if this were a 2-dimensional function, then you know that there are actually 2 derivatives, 2 partial derivatives. So it would have the type pair double, double, double. And we'll see an example of that. But as you can see, it's pretty easy to define. All right, so we can apply a sine test to some value, like 1. Can everyone see that?
Yeah.
All right. And we get some value, so 0.84, and you see it says d, the value, and then dot, 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 representing the infinite number of derivatives that are after that. So, I don't know, if I did pi on 2, we should get 1, okay? Now, everyone knows that the derivative of sine x is cos x, right? And then the derivative of cos x is negative sine x, and then the derivative of negative sine x will be negative cos x, and so on. And it will continue like that forever. That's just that particular function. So you keep taking derivatives of it, and just go through that sequence of sine, cos, negative sine, negative cos, and so on. So, D is my derive operator. It's implemented as derive at basis x unit. So in this case, the linear map is just a, it's not even a map, it's like a constant map, and you don't have to worry about it. But if I do that, you'll see I get a value very close to 0. Floating point again. Then if I compose D with D, I get, oh, it's a -1 now. And now it's something close to 0 again. And then, and so on. But see, you know, this is, I can do this at any point on the curve, in the function. And it doesn't matter. And it's just an infinite series of, an infinite tower. Now that's not so interesting because that one's periodic, right? You might think there's some trickery there. But how about one that kind of has a finite number of derivatives before it goes down to 0? Let's have a look at a polynomial. So I define, so you need this thing called IDD. It's kind of your way of injecting a variable into the derivatives. But you've got IDDx, and then we've got 3 times x cubed, 2 times x squared plus 5x plus 1. And I've written out what I think the first, second, third, and fourth derivative are. You can check my work. I think it's right. Have I made any mistakes? Hopefully not. So now, I'll go back to the window and we'll just run polytest at, say, the value 1, and we get 11. I can do this over here. Okay. So that should be right. So it's 3 plus 2 plus 5 plus 1. Okay. And so before I do this, what do you think the derivative of polytest at 1 is going to be? Let's see. Yeah, I agree. Okay, so it's 18. What do you think it's going to be at the second derivative? Oops, sorry. So it should be 22, and then 18 again, coincidentally, and then 0. And then 0 for every single one after that. But you can keep on taking derivatives, it doesn't matter. So, do look up the paper and how it's done. I'll give you a bit of a clue as to how it's done though, it's quite clever. This is actually from the library code. Actually, I had some, let's go down to the num instance. That's only interesting for the multiply has this distrib here, and that's actually applying the distributive law. So that's kind of clever, you know, the distributive law from calculus. But let's have a look for sine, and now we'll see that along with each function, we actually keep its derivative as well. So for sine, we bundle it up with cos. With cos, we bundle it up with negative sine, and so on. And each time a derivative is done, basically you create some kind of function out of this by adding them together and so on. Each time you do a derivative, it's just adding together then the actual the derivative of it. But then it kind of recreates it and bundles that up with the next one and so on. And that's the trick behind it. And so it is symbolic rather than numeric. That's how it does it, which I think is really clever. Anyway, good little library. And I'll just show you surface test finally. This takes like 1, 2, and you get some value, and then you can either do dx or dy. So that's ddx, and that's ddy. You get 2 partial derivatives that way, and you just keep going. So that's how we calculate normals. So it's used inside the library. It's orthogonal to the Shady library, though. All right. But it's a great little library. And what really blows me away about it as well is that pretty much the entire implementation is just in this McLaurin.hs. And that's not a whole lot of code. Just by getting down to the very essence of what differentiation is, it's managed to sort of write it in one module. I think that's really impressive.
Yeah, those types are super straightforward.
Yes, that's the other problem, right? Is, when you want to make stuff general in Haskell, you do have this problem of having a lot of constraints, and I don't know what to do about that. Maybe that'll be improved in future programming languages. But at the moment, I do find when I'm programming in Haskell, it's sort of is getting to that stage where it's like, it's just pushing the boundaries just a little bit too far with this particular language. Yeah, and we might not want to go any further.
So what you're saying is Haskell is not quite general enough for you?
Well, I have seen in independently typed languages that they've managed to collapse some concepts down to a simpler unifying concept. So now in Haskell, it's kind of fun. What the hipsters do is they do type level calculations, like adding together numbers in the types, you know, and it can be pretty cool to do. But in some of the newer dependently typed languages like Agda, Idris, and so on, you can actually that distinction between type level and value level has actually been removed. The same thing. This, of course, means that your type checker can sometimes not terminate. It might not be a good thing, but that's what happens. But the programming in the languages seems to be easier. So where is this? Where's the mirror? Oh, here it is. It's not too much longer to go in the talk. And I'll show you some, we're getting up to the bit where I show you some fancy graphics, so hold on.
Such a pixel tease, Sean.
That's right. Okay, so embedded domain-specific compilers. Shady is one of these. Not an EDSL, it is an EDSL, but it's also a compiler. It's like an EDSL plus. Okay? What you do is you write programs in Haskell, but instead of them directly being executed, what you're actually doing under the hood is you're producing an AST instead. Okay? And you can use the AST to produce the GLSL code then. So it's almost like you do the complete back end of the compiler, but you still take advantage of the host language's type system, and you don't have to write a parser. So you do save a little bit that way. Now I was going to provide a tour of this. I'll try and keep this quick.
So who wants to do a talk on Agda or Idris?
It's got to happen.
Yeah.
That would be really
We bring it up seriously every month.
Sorry, Sean, I'm just going to...
Okay, so I'm just going to take you through a short tour of like a cut-down version of the Shady compiler, just to sort of show the embedded domain-specific compiler concept. Not actually going to go into code generation, but I am going to go into abstract syntax tree generation. So we have a really, really quite simple expression data type, E here, which you have four alternatives. You either have an operation, a variable, application, or lambda. Okay. And in the operations, we have literals, the adding of two floating point numbers, pairing, and first and second. I just decided to stick those ones in, just so I could illustrate some concepts. A real language would have a lot more in it than that. And then we have this interesting type, in which it seems a bit funny, but you have like this primitive float t, which is type float. So what's that? It's a thing that just signifies that something's a float. And then we've got a pairing combinator, well, pairing constructor, I should say, and also a function type constructor. And the use of this is that you can reflect the types of your expressions into a data structure, and then this helps with code generation. Okay, so you can actually write a function which can then do stuff based on the structure of the type. So it's a fairly modern sort of trick, and you can see I'm using GADTs here. Is everyone familiar with the GADT syntax? No. Okay. Right. It's quite different to normal data types, and the only thing that's really different about it is that the result type can be different to what the type variable is. So, I mean, another way to write this. Another way to write this is just as E8. I think you can do this as well. Yeah, that's okay. So that's your type variable, but you can have different result types here, and so that's, I think, clear in this application here, is that you can produce something of type EB. Wait, I can explain this much, much better. So let's look at a normal data type declaration, like list of A's, which is nil or cons of A, some list of A, right? Okay, so that's your normal one. If you were to write this as a GADT, you'd write it this way. And you'd say that cons is the constructor which takes an A and a list of A's and produces a list of A's. And nil is the constructor which just produces a list of A's. Okay? That's the totally equivalent GADT representation of it. But what's interesting about GADT is you can actually change the type at the end. And one of the useful applications of this is to create typed interpreters. So you could create like a much simpler language than the one I've got here. Like it could be add two expressions together, and you could have some kind of if expression which takes some expression and produces, and then does this expression or that expression. And that could just be your language, right? But unfortunately, it's not typed. Okay, and that's kind of, so you might go, ooh, well, I could add a type variable. That'd be really cool. And then I could make sure that you only ever add together two things of the same type. That works fine for adding. That's fine. So if you add something in xbay to xbay, you get back another xbay. That's the type. Woo. But it doesn't work in the if case because you really need this to be xbool. Using a Boolean value to select between two different things of arbitrary type. You know, it's like, you know, if, I don't know, x is greater than 1, then, I don't know, return this string, otherwise return another string. You can see that the types are kind of different. So you can't actually do that with regular types, but what you can do this as a GADT. So then that will have this type, and then if E will have this type, which looks really, sorry, with the arrows in there. Right? That looks pretty weird because you've got this X Boolean here, but you're allowed to do that with GADTs, and that's why they're really cool.
But also,
Yeah.
the other thing that's really weird is that because these are not functions, they're constructors, you can deconstruct on them, and then when you deconstruct on them, that will propagate the type information.
That is true.
back
When you do a
into your
case
bound
expression
patterns.
on these things, at the point where you do the pattern match, so if I write something like this, foo of some expression equals case x of, and then where I write if E Boolean then else. The really interesting thing is, at this point, compiler type checker knows B is bool here, which is cool. But it doesn't know anything about then and else at that point. It knows that then and else are some expression of some type, some egg. But it actually knows at that point. And if you tried to do something with that Boolean that wasn't a Boolean, that wasn't a Boolean function on it, then it'll give you an error message. One of the really nice things about this is when you normally write an interpreter, you can write it incorrectly in the untyped case. So you can write an interpreter where you have to basically somehow check what the value is. So when you run the expression and it's supposed to produce a Boolean, but it might not. And so, yeah, you have to write this extra case in your interpreter which checks whether it actually is a Boolean. And if it's not, it causes a runtime error. This way you get compile time guarantees. Anyway, we're basically using these GADTs for that very reason. So that when we create these expressions, they're typed in Haskell, and they're going to be type correct, and then you can't, yeah, that's why we're doing it.
Yeah. So, Sean,
Yes.
just do in the interpreter, if you do like T lam in that case, like : T lam,
Yes.
or any other thing
Yes.
if you just type it.
Right. Like this colon T land. Yeah.
Yeah. You can see that the type that it has is the same one you identified, but it is a data constructor because it has the capital letter. That's the kind of the magic of it all.
Well, I mean, if you do type of, say, cons operator, you get that. You can always do the type of constructors. You can do the type of, say, left in either, and it will tell you that it's A to either AV. You know, so it's,
yeah, but it has a weird type. That's what I mean.
it does have a weird type, not what you would normally expect for a constructor. But it turned out this theory could be generalized. It turns out it has applications, and that's why it's in Haskell now. So yeah, that's the language. It's really, really simple. But then I have some convenience functions here, which I use to create pairs and take the first and the second. And that's kind of nice. And then I define this num instance as well on expressions that have a float type. And so this way I can just type in the literal one, and it'll actually get turned into a float literal without me having to type op lit from integral x. I can write the functions in quite a natural way. So here, I'll just go down to the bottom. Down the bottom here, I've got a test function, and you can see that it goes from a pair of float expressions to a float expression. And I've written it just in a totally normal way. And that's because I overloaded the plus operator. And here, where I've got this literal 1 and this literal 2, that as well, it gets turned into an expression, turned into a float literal. There's only a couple of things I wanted to show you here, which is that when I type test, I'll say no instance of a function, but say I apply it to 1 and 2, like this. Look at that. That there is an expression. That's the AST basically, and then you can use that to generate the GLSL code. So this is basically the embedded domain-specific compiler approach. Just to reiterate the point, is that you're not producing something that's executable, you're producing something that produces an AST, but it's still very convenient to use. So when I showed you those expressions, those slides before that showed you the 3D functions, and I said I was lying a little bit about the types, they're actually producing these ASTs under the hood. They're not actually working on regular numbers and so on, and regular triples. Yeah. Although the language is kind of simple, this is the final thing I'm going to show you here. Although the language is kind of simple, you can kind of extend it by writing. There are these two classes called to-e and from-e, which are defined. Where are they defined? Up here somewhere. To-e and from-e, and basically that gives you a way to inject values into an expression and then take something out of an expression. And why this is useful is that, for instance, I might want to write functions on complex numbers, and it's not a very good interface, but some complex and it's got two A's in it, and then all I have to do is write these two instances, and then what I do is I get this function here. Now this doesn't directly produce an AST, right? So higher level, if I type higher level complex 1, 2, no, that did actually work. Okay.
It's not often that something accidentally does work and does type, so cherish this moment.
That's right. Yeah, no. But let's have a look at what the type of that is. Well, it should just be expression flow, shouldn't it? That's what it is. Yeah. No, okay. Of course that was going to work. But the problem is I can't actually have in the language. So the way that the compiler actually works is it takes these functions and then it partially applies them to a bunch of dummy variables, which actually then become the uniforms that I talked about earlier. But the problem is I can't actually just apply high level to a type like that, and I'm just getting a type error, although I can do test applied to some variable. Sorry. What I have to do first is run this compile function on it. And a type of, so if we look at the type of test again, we'll see that it's a pair of float expressions to a float expression. But if we look at the type of float compile test, type of it, you'll see, now we've got some annoying type family stuff in the way. I really wish it would simplify this. It's real float. I'll just prove that its type actually is this, because it won't throw a type error. There we go. So if I'd done that, it would have gone, no, it's not. That's not true. But now I've simplified it for you, okay? So it's actually, it's an expression of a pair of floats to a float. Now it's slightly different. Now why do I want to do that? Because we actually have pairs in the well, I'm pretending that GLSL has pairs, and actually it kind of does. It has these vectors, and a two vector can be a pair. You can use it as a pair. So what you do is you compile it first, and then you apply it. Then you apply it to a variable, and then you get this expression here, which is just add float first of var vx applied to second of var vx. Beautiful. And that's actually pairs in the language, as in the target language. It's AST that we're constructing. And the nice thing is that because I wrote those 2e and from e instances for the higher level thing, compile that and apply that to a variable, and I get something of exactly the same type, and I get exactly the same expression as well. So it's converting that complex value into a pair, and that's just nice. So, and I can do that for, you can write your own data types, you can write your own 2e and from e instances, and you can use that with your language, so it's extensible as well, which is kind of nice. And that's all I've got to say about the compiler. And I hope that gives you somewhat of a flavour for how embedded domain-specific compilers work.
Sorry.
Yes?
Just what you said about dummy variables, or you apply.
Yeah, I know that sounds really funny. So basically, the function is an effect. The function specifies some kind of effect, and the input to it is going to be any number of things that define the surface, like the radius, the width, the height, whatever. And then, of course, there'll be the actual point that you're sampling at as well. And for the first few, which define the surface in some sense, like width, height, etc., you want to pass those in as uniforms. So they're constant for one frame. And for the point that you are sampling the surface at, that's something that goes in the vertex shader, and that's called an attribute variable in GLSL. And basically what you do is you partially apply to dummy variables for the uniforms, and then you partially apply to another dummy variable for the mesh attribute as well. And then you get something which isn't a function anymore, it's just a complete AST, and then that gets turned into some code. And then you just make sure that you put the right variable declaration.
So you just recognise the variables when you see them later?
Yeah, you give them a name which is just unique.
Oh, okay.
And then, yeah, you make sure these dummy variables have a unique name, and hopefully meaningful names as well, like I give them meaningful names. And then that will produce this GLSL code. And then you just make sure that you declare all those variables at the top, because that's basically how
so you basically
it was too small.
You're just feeding in your GLSL parameters basically into that.
Yeah, that's what I'm doing. So the implementation technique is that I've got to generate a vertex shader which expects certain variables. The way I do it on the Haskell side is I partially apply these dummy variables, thus inserting it into the generated code. It's just how you do it. Yeah. Yeah, so like, you would expect words like width and height and so on to appear in there, and then you just make sure that you pass a value into the GLSL shader that way. So now, let's go to the graphics. It's time to do this. Is that a load of memory thing? Okay,
It's all good.
okay. Right, so just quickly, I've called this Max Shady, which sounds hilarious when you say it in a Scottish accent. It's a Haskell/Cocoa front end to Shady, which is the language. The GUIs and the OpenGL stuff and the OpenGL context are rendered in Cocoa. And all OpenGL commands are actually done in Haskell via Sven Parner's OpenGL library. FFI is used to communicate between the two, which actually isn't that hard. Surprisingly, the bulk of the implementation effort was just, me learning Objective-C and learning Cocoa, and it was annoying. Let me tell you that. But learning anything new is annoying, so I'm not going to blame Cocoa that much for that. And I have this thing called a UI monad, so it's one more level of abstraction. So what I wanted to be able to do was generate interactive effects where you can actually change certain parameters at runtime. So it could be the radius of a sphere, for instance. And a nice way to do that might be to have a slider where you sort of move it between the small and large values and change that. So then I basically created something called a UI monad where you can generate these. It's basically a data structure which I've made to be a monad so that you can use the monadic syntax with it. But it allows you, as well as specifying an effect, to also generate new values, and these new values are sliders. And I might arbitrarily extend that with other things like checkboxes, buttons, whatever I think might actually be useful. But at the moment it's just sliders. So now it's time to show you the demo. This is the end of the talk after this. So thanks for your patience. But this will be the fun bit. Okay, so test effects. So in future, I'm not doing this yet, to use libghc to compile code on the fly and turn it into an effect. At the moment, it's all pre-compiled and baked in. But what I want to do in future is open up the application and say, go up to the file menu, click on open, specify this Haskell file is the source code for this effect. It compiles it, puts it on the screen. Anytime I modify it and it compiles successfully, it changes it instantly on the screen so that it's just so you have instant feedback. So I'm going to start off with just looking at, say, the XY plane. And you'll have to bear with me while I compile this. It doesn't take too long. That's terrible. Yes, okay. That's the XY plane, and in this thing I can rotate it around and I can zoom in and out, okay, arbitrarily, which is kind of nice, but that's pretty boring. And there's no UI for this one. But that's the way that was defined. Okay. So now I'm going to show you an effect which is a torus UI. And basically I start with the do notation, then I say that inner is a UI slider float. I give it a label, inner. I say it goes from 0 to 1. Default value is 0.3, and then I put this nothing here. That can be just something, and that's the number of ticks if you want it to be move up in discrete jumps. If it's nothing, it's continuous. And I have an outer as well. And then what I do is I return this thing here where it's a torus applied to the outer and the inner. That torus is that one I showed you on the slide before. So I'll now just make sure I compile that one. Close the old instance. And there's our torus. And we can rotate it to our heart's content. It's got a bit of drag there. And you can zoom it in and out. And then you can play with the parameters. It's really fast. You can see my menu meter up here. It's barely using the CPU at all. It's basically all happening on the graphics card, which is really cool. So you can play around with that. And then I've only got one more example I'm going to show you, which is just this flower UI. And I really haven't had enough. I've spent so much time implementing this that I haven't actually played around with it that much. But this effect that I'm about to show you is really pretty. So it's a torus composed with a height field. And the height field is two cos waves going at right angles to each other. So it looks like an egg crate, if you can imagine that. Right? Sine waves this way, sine waves that way. Kind of a Ripley thing. That's the height field. And then what we do is we compose that with the surface of the torus, creating if you can imagine wrapping that egg crate around the torus. I don't know why I'm explaining it to you when I could just show it to you. Let's show it to you. Let me close the old instance. All right. So there's our torus, and I've put the spike height, as I've called it, to 0 on purpose. But as I move this slider, you can see it deforming. Sorry, it's going outside the bounding box there. You can see it's deforming. And then what I can do is I can change the periods in the egg crate. So at the moment there's only 2, 3, 4, 5, whatever you want. Make the spikes really big. Spin it around. Change the radii. Let's make it small, that big. Yeah. Some really beautiful stuff you could make with this, I imagine. I think this would be really useful for making just like pure mathematical objects that have a lot of structure to them. So, you know, not so good for your everyday artist, but for nerds like us, it could be really nice to make some cool art with. Still a lot of work to do on this. I've only got sliders and, you know, I haven't got it actually compiling code, but it's not that much implementation to do soon, and I hope to release it kind of soon. And yeah, that's the end of my talk. So, got any questions?
Yeah. So the space of